Start recording. Alright everybody, here's a couple videos I'm going to make today. This one's going to be about the Chapter 4 homework and some probability stuff you might have to need, or you might need to use with that. I'm using new recording software, so if there's any trouble with this, I'd really like to know ASAP. So, here we go. Let's just run through this. Alright, minimize that. Yeah. Okay. Yeah, so I'm going to do a bunch of these. Let's start with this one. So what do we have here? 63% of homes have garages. 63%, or we could say 0.63. Pools. We got 30%, or we could write it as 0.3. And we have both. It's 8% or 0.08. So whenever you're given a situation like this where I have two categories with overlap, what you need to do, hold on just a second. There we go. What you need to do is draw a Venn diagram. So here's the universe, and here's garages, and here's pools. Right, and here's the overlap. The overlap is 0.08. I think that's too small. Hold on. Okay, how about that? Yeah, this is as big as that gets, I'm sorry. It's all about how much software and how much I need to pay for it. Alrighty, 0.08 in here, a little bit easier to read there. 0.3 over here. And so what is the probability of having a pool or a garage? So what does this say? In math, this looks like this. Probability, curly P for probability, G for garages, a big cup or a big U for or, the garage or pool. So the formula we're going to use for this is probability A or B is equal to probability A plus probability of event B minus probability of them occurring at the same time. When you think about this, right, that 8% is included in both of these, right? So if we just added these together, that 8% would get double counted. All we're doing here is subtracting off one of those 8%, so we're only single counting the intersection. So off one copy overlap is how I talk about that. Yep. Okay, so what is this? This is going to be probability garage plus probability pool minus probability pool and garage. So this one's 0.63 plus 0.3 minus 0.808. Excuse me. Oh, and I don't know if you picked up a calculator and did 0.63 plus 0.3 minus 0.08. You get an answer of 0.85. That's the proportion that have either a garage or a pool. So 0.0, not 0.85. And that's how it goes. That's how it does. So let's contrast these two statements. This is why I wanted to do this problem. Erase that, please. Okay, so this says probability of having neither a pool nor a garage. So So if the chance of having one or the other is 0.85, the chance of having neither will be 0.15. They're just reflections or complements of each other, as we say. Okay. Okay, so what's the probability of having a pool but no garage? Okay, so 30% have a pool, 8% have both. So the probability pool, no G, no garage. Let's see. Let's give that a try with 0.3 minus 0.08 would be 0.22. Right? Yeah, there we go. Okay, so a couple questions there I thought were kind of important to talk about. I'm going to lather, rinse, and repeat on these. I'm going to try and hammer a lot of examples. I know this will make the video longer, but you know, I want you to see a lot of these and a lot of when you use what, you know, that kind of thing. Okay. So problem 2 is another Venn problem. And I'll be doing 1, 2, 3, 4, 7, 9, and 15 if I'm lucky. Yeah, okay. So, college dorm rooms, large campus. So what do we have? 36% are refrigerators. Have TVs at 57%, and the overlap is 20%. Okay. All right. Let me know if you guys can read this. I'm imagining you're going to full screen this video, but if your laptop is, you know, one of those tiny little MacBooks, that'll probably look pretty small. I'm not sure. Yeah. So anyway, to update me on whether or not you guys are able to see this. Okay. Refrigerator, but no TV. Well, 36% have refrigerator, minus 20% have both. What's that going to be? 16%. And remember that I'll have to put this as 0.16. Thank you, Pearson. I know, I'm just brilliant. Okay. Okay, so refrigerator or TV, but not both. So this is different than refrigerator or TV, right? Back here we subtracted off one copy of the intersection so that we had garage, pool, or both. Now we're going to subtract off 2 copies of the intersection so that we don't have any overlap. So 36 plus 57% minus 40%. And, you know, like, I could pretend that I can do math, but, oh, geez, I don't know. It just takes so much energy. I got this calculator sitting right here. I want to keep all my brain power for making decisions about which part of the workbook to use, not about, you know, arithmetic. Alrighty. Probability of having neither a refrigerator nor a TV. Okay. So this was but not both, right? This is neither nor. So this is not going to be, we're not going to do the reflection of this. We're going to do the reflection of the or probability. So let me just recalculate here. 36 plus 57 minus 20. 36 plus 57 minus 20. All right, so 73% of people have one or the other or both, meaning that 1 minus 0.73 equals 0.27. That's the proportion of, what is it, dorm rooms? Rooms with R, no refrigerator, right? R chick, no refrigerator, and no TV. Okay. All right, we're doing good here. Okay. I'm not gonna complete this problem, but I want to give kind of a speech about row column totals, etc. Excuse me. Okay. So we got some data, right? We got countries A through E. And what do we have here? The number of people reporting their completion. Okay. So, if you see in the subjects on the test, I would have classified this problem as a marginal distribution problem, not as a probability problem. So that's the keyword you would search for if you were doing a search on the e-text. Someone did ask me, could I also list the chapter numbers next to the subject numbers or the subject descriptions? And the answer to that is no. As part of being a good successful college student, you have to get comfortable searching texts for the right subject. I'm sorry, you're not in high school anymore, and that is a requirement for good study skills. That is just part of being a good studier, is being able to look in the index, look in the table of contents, or if you have an e-text, use the search button to find the subjects you need. And so, if you do that, you'll feel more confident on the test, I promise. That's part of taking ownership of the knowledge you're acquiring here, instead of just expecting me to feed it to you. Okay, so what does this say? This says, what's the chance somebody's from country E? So, this is why it's called marginal. I'm going to look in the margins over here, right? That's everybody from country E. That's everybody at all. So the chance that I select someone from country E is just going to be 1549 divided by 7696. Oh, and if I picked up a calculator, 7696. Yeah, about 20%, round to 4 decimal places. Okay, so what I'm getting out of this is 0.20127, so we'll make that 0.2013. Thank you, Pearson. Okay, so you guys see what's going on there? Depending on how they're asking the question, you're going to look at one margin or the other, right? And if it asks you, what's the chance I sample someone from country A who is a postgraduate, that would be a cell total kind of thing. So 6 divided by the total down here. Okay, like if I selected someone from the survey at random, what's the probability that his or her, what's the probability that they completed their education before college? So high school or primary, right? So it's these two divided by this number there. I add those together. Out of a total. So these are the two outcomes that get me someone with high school or primary education or less, right? And these are the total samples, the total size of the total number of people I could have, right? So number of possibilities getting the outcome I care about, right here, and outcomes at all, right? Number of outcomes at all. Okay, so 4190 plus 1185. Divide that by 7696. And I'm going to get 0.6984. And next digit's a 1, so that's my round. That's weird. Oh, 6984. Yeah, thank you, Pearson, I know. Alright, so I'm going to move on. It's always something like that. It's always something like that. Like in this case, right? What is the probability that a person is from country B or did some postgraduate study? It's going to be a little bit of a bin. Yeah, there's some overlap there. So yeah, that would be like applying our probability formula, which I'll be giving you guys on the final. Event A or event B is event A plus event B minus probability of A and B. So if we notice our disjoint independent language here, this is 0 equals 0 if disjoint. Probability of A and B happening at the same time is 0. The A and B are disjoint events. They can't happen at the same time. Which means that if I do this calculation, A or B, and I get just probability A plus probability B, I know that I've found a disjoint pair of probabilities. Okay, similar thing happens if I do this. If this equals probability B, multiplication's commutative, whatever. If that equals the product of the probabilities, this is independent. If it comes out like this, A and B is probability A times probability of B given A, right? This is the actual general formula for the AND rule. But what do we know? We know if independent, probability of B given A is just the same thing as the probability of B, right? So these when you see that it's probability A times probability B, like for card drawing or anything like that, what you're actually seeing there is an example of applying this formula in the special case that my events are independent. Okay, bit of a digression, but I was going to have to talk about it sometime, so there it is. Apparently my voice is not quite back yet, so I'm going to jump to the problem I think is most important to talk about here. Actually, there's two of them. I've got to do two of them. We'll see if my voice holds out. Nope, not that one. Nope, not that one. Must have been 7. Okay, yeah. I do want to talk about this one just a bit. Okay. So this one is nice because it provides us an opportunity to use our given probability formula. So if I have A given or given B, what's the chance of A happens? Let me actually make that an A instead of an H. I do apologize for my handwriting sometimes, but let me just show you how long it would take for me to write well. Yeah, so it's not worth it, right? Okay. Probability of A happening, event A happening, given that B already happened, that's the probability of A and B occurring at the same time, divided by the chance of A happening, or sorry, of B happening at all. Chance of B happening at all. Okay. So, usually we see this formula after we've drawn a tree, but I want you to notice something here, right? So, probability of, so what is this? 60% have fever. So, probability you have a fever if you're sitting in the doctor's office is 0.6. If you have a fever, the chance that you also have a sore throat is 0.3. So, and it says probability fever, whoops, about to write an or there. Probability fever and sore throat. It's a good thing we got this formula, right? Because what are we given? We're given probability sore throat given fever, and we know that's going to be equal to probability fever and sore throat divided by all of the ways to have a fever. Well, the probability of having a fever, probability of a fever, that's 60%. This is 30%. So what do I have here? I have 0.3, just a substitution there, is equal to the probability both at the same time divided by, oops, not there, not there. I'm looking for that one. Substitute that in there, 0.6. Oh, so if I multiply both sides, 0.6, I would have the probability fever and sore throat at the exact same time is 0.3 times 0.6. 3 times 0.6, 0.18. 0.18. All right. Anybody think it'd be higher? I don't know. I didn't really have a guess on that one. Okay. So important to go through that because I thought it was a nice way to touch on another way to get at things, right? Okay. So, let's see here. My voice seems to be doing better. I'm gonna keep going. 3? No. What is it? Okay. Yes, this is the one I want to talk about. This is going to be my example of how to do a probability tree. There's a spot on the workbook for it. Just based on how uncomfortable my statistics students, whoops, this is test 3 workbook. Okay, so, good review. How do I get the final exam workbook? I go to As You Learn, I log in, I look at my class, and I scroll down to the bottom where it says final exam workbook. I pop that open, yeah. Okay, so there is really, really seriously some way in here to calculate probability trees. There it is. Based on how uncomfortable people are with naming things and substitution, I do sincerely believe it would be easier to do these by hand. Yeah. So I'm going to show you how to do one by hand. All right, here we go. Excuse me. Okay. So we're flying from Boston to Denver with a connection in Chicago. So this is all about first flight leaving on time. So my events are on time, first flight, and luggage arrives. Luggage arrives. And what does it say? It says, if the flight is on time, the probability that her luggage will make the connecting flight. Okay, so luggage, luggage arrives, luggage connects, all the same thing, right? Luggage makes it 2. Okay, so, let's do a tree. Again, you don't have to decide, or, it's not important whether you use on time or luggage arrives first. You just proceed. It'll work out. Okay, so I could be on time, or I could be not on time, right? That chick means not on time. And if I was on time, That would be 15%, right? 0.15 there. And so these are always complements. Minus, right? Call it like 1 minus x. Each complements of each other. So that's 0.85. I usually do those in my calculator. I know it's a simple subtraction, but again, save your brain power for, things a computer can't do. Okay, so my luggage could get there, or my luggage could not get there. My luggage could get there, or my luggage could not get there. So what does it say here? It says, if the flight's on time, the luggage arrives 90% of the time. On-time flight, luggage arrives 0.9. So this must be 0.1. Again, complements. If I'm not on time, there is only a 55% chance my luggage arrives on time. Okay, so this must be 0.45 down here. Okay, so these are ands, right? This is probability on time and luggage arrives, and I would multiply these two together to get that, right? So that would be 0.15 times a 0.9 is a 0.135. This one's 0.1 times 0.15 is a 0.015. Down here we got 0.85 times 0.55. 0.465, and that's important because they're going to ask us for 2 decimal places in a second here. 0.85 multiplied by 0.45, and I'm just kind of prepping out this so that once we're actually answering the questions, it will be we'll already have this information in front of us. 2.5. Okay, so first question. Are the flight leaving on time and luggage making it to Denver independent? And so for that, we ask ourselves the question, probability A given B, given B, is that the same thing as probability A? No. If I arrived on time, I have a 90% chance. If I didn't arrive on time, I only have a 55% chance, right? So this is not the case. Therefore, independent. Yes. So, are they independent events? No. The probability that the luggage arrives with her depends on whether the flight is on time. Boom. Final check. Thank you. Okay, so what's the probability the luggage arrives in Denver with her? Okay. So what would that be? It arrives on her if we've got on time and luggage arrives, or if we've got not on time and luggage arrives, right? So there's 2 and probabilities there. They are disjoint, right? I can't be on time and not on time. So these are disjoint. So when I write this, probability on time and luggage arrives, or on time not and luggage arrives, I know that the other side of this formula is just going to be these 2 probabilities added up together. In other words, probability on time and luggage arrives, 0.135, plus not on time and luggage arrives, 0.4675. And if I do that, 0.135 plus 0.4675, I end up with 0.6025. 0.6025. And there it is, guys. There it is. That's how you do as a tree. You calculate your and probabilities by multiplying down the branches. Then it's just apply formulas. You got 3 formulas to look at. Probability A given B, probability A and B divided by probability B. You've got probability A and B is either. So probability A times probability B for independent, and that's equal to probability A times probability of B given A or not. Okay. And then just one more, probability A or B, probability A plus probability B minus probability of both happening at the same time. That's 0 if disjoint. Okay, guys, I got students showing up for office hours. My voice already crapped out once during this video, so I won't torture you guys with my throat clearing anymore. I hope that helps generate some comfortability about probability. We'll see if the quality of this video is up to snuff too. Alright, yeah, please give me feedback if this new software worked out any better than the old stuff. Alright, thanks everybody. See you on Monday.